The universe is full of secrets, and one of the most powerful forces shaping it might be carried by something unseen. Gravity, the force pulling everything from planets to particles, could be delivered by an invisible messenger, graviton. Scientists believe this particle could explain how gravity works at the tiniest scales, linking it with the quantum world. Unlike light or electricity, gravity reaches across the entire universe, yet we don't fully understand how. In this video, we'll explore what gravitons are, what makes them so strange, and why they matter in our quest to understand everything. Though only theoretical, gravitons carriers play a key role in some of the most important ideas in physics. They are a logical outcome of efforts to explain gravity at the quantum level. No detector has seen one, no experiment has caught a signal, yet the idea endures. Researchers persist because it fills a major gap between general relativity and quantum mechanics. If proven real, it could transform physics. Like atoms before microscopes, these particles may simply be awaiting confirmation. Their absence fuels deeper inquiry. Living at the edge of what we can observe, they pull us closer to unifying knowledge. Explaining gravity as a force mediated by particles introduces a radically new view. Just as photons carry light, gravitons are believed to transmit gravitational influence between particles. Quantum field theory describes forces as exchanges of such messengers, and this one fits naturally into that framework. It tells matter how to move through space, placing it in the same family as gluons and other bosons. While other forces are well accounted for in the standard model, gravity still stands apart. This idea helps reimagine the gravitational pull as an interaction built from quantum information, no longer just a bend in space, but a quantum conversation. Gravitons are expected to carry a spin of 2, making them unique among known fundamental particles. For comparison, photons have spin 1 and electrons have spin 1/2. That spin value leads to complex interactions with the universe. It's not just a label. It comes directly from the equations describing gravity in quantum terms. Only a spin 2 entity fits the shape of those interactions. This specification influences how gravitational waves behave and how the field itself might ripple at the quantum scale. Their spin is more than a trait. It's a mathematical necessity that bridges vast and tiny realms. Predicted to be massless, the particle must move at the speed of light, enabling gravity to stretch across cosmic distances. This absence of mass is critical. If it had any, the force would weaken rapidly with distance like other forces do. Instead, we observe gravitational effects across galaxies and beyond. Being massless aligns it with particles like photons, giving it infinite reach. This property fits with Einstein's view of gravity as a smooth field, and with quantum theory's need for discrete carriers. Its weightlessness isn't just a feature. It's essential to how the cosmos holds together. Gravitons are also electrically neutral, unlike charged particles that interact with electromagnetic fields. They move through matter silently, affecting all things equally. This neutrality explains why we can't detect them with instruments that rely on electric or magnetic responses. Gravity doesn't discriminate. It pulls on everything the same way, whether it's charged or not. That behavior supports Einstein's vision of a force that's universal and impartial. The quantum version must be just as fair, moving unseen and unbothered by the properties of what it touches. A unique feature of these particles is their ability to interact with one another. Unlike photons, which pass through each other, gravity's carriers could affect others of their kind. This self-interaction creates feedback loops and complex behavior. It's one reason why gravity is so difficult to model in quantum mechanics. The math becomes deeply tangled. Each unit doesn't just transmit force, it reshapes the space where all interactions occur. Understanding this recursive, self-influencing quality is essential for a complete theory of quantum gravity. Gravitons are also believed to couple with matter extremely weakly, making detection almost impossible. Unlike photons or electrons that leave measurable traces, they slip through matter without a sign. That's consistent with gravity's status as the weakest of the known forces. It controls planets but barely influences individual atoms. This quiet behavior aligns with theory. It explains why no detector has found them yet and why future experiments face enormous challenges. They whisper instead of shout, which is why they may have escaped us so far. Another predicted trait is complete stability. They don't decay or change form, allowing them to carry gravity without interruption. This eternal lifespan ensures that gravitational effects remain constant across time and space. Without stability, galaxies wouldn't hold together and the force would waver. A stable carrier supports the consistency of pull across billions of years. Their unchanging nature reflects the enduring power of the force they represent and aligns with the persistent structure observed in the universe. Classified as bosons, these theoretical particles can share space and create overlapping effects. That's why gravitational fields appear smooth and continuous. Bosons reinforce rather than cancel one another. This trait allows the force to remain steady over great distances. Just as photons form light waves, these units could build gravitational fields through their collective motion. Their bosonic nature aligns with Einstein's elegant vision and strengthens the case for treating gravity as a wave-like quantum phenomenon. Because gravity acts over vast scales, its messenger must be both massless and neutral. This combination allows the force to stretch across space without fading. Unlike short-range forces, gravity maintains its influence from planet to planet and galaxy to galaxy. These traits make such a particle a strong candidate for explaining why gravity behaves so uniquely. Its range turns a local phenomenon into a universal connector, transmitting information across the structure of the cosmos. In quantum field theory, the idea arises naturally when applying established principles to gravity. Just as photons appear when quantizing electromagnetism, a spin-2 massless particle emerges when gravity is treated similarly. It's not an invention, but a logical result. Seen this way, it becomes the smallest ripple in the gravitational field, much like a photon is in the electromagnetic field. Its existence is predicted not from speculation, but from extending tested methods into new territory. Einstein described gravity as the bending of space-time. The quantum version imagines that curvature broken into the smallest possible pieces. Each of these ripples would represent a minimal bend in the cosmic fabric. That makes it not just a feature of space, it helps define space itself. This view links the smooth curves of general relativity with the discrete steps of quantum theory. The result is a new way to see motion and structure, not as flowing lines, but as countless tiny moves. In string theory, the graviton appears automatically. It's the vibration of a closed string, not something added by hand. That makes it unique among theories trying to unite quantum mechanics and gravity. Its appearance supports the idea that space and time emerge from deeper structures. These vibrations suggest a hidden layer of the universe built from loops and resonance. In this context, the graviton isn't just a force messenger, it's a clue that the building blocks of reality may be more musical and strange than previously imagined. Gravitational waves are massive cosmic ripples, but at the smallest scale they're made of individual quanta. Just as light waves consist of photons, these are thought to be formed by gravitational particles moving in unison. Detectors like LIGO confirm the wave's existence and offer indirect support for their quantum nature. Though we haven't detected individual units, the presence of the waves themselves hints at what lies beneath. Their properties explain how space-time stretches and compresses in response to immense energy events. Each wave could carry the fingerprint of a quantum structure. Have questions or wild theories? Drop them below. We're reading. And if there's a topic you want us to explore next, let us know. Your idea could shape our next video. Thank you for joining us on this journey through gravitons. Please like and share the video, and if this video helped you understand something complex in a simple and clear way, there's a lot more where that came from. We break down big ideas into easy explanations that anyone can follow, no complicated jargon, just straight answers to fascinating questions. Join us to keep learning in the easiest and most interesting way possible. Whether it's science, space, technology, or just something you've always wondered about, this channel is here to explain it all. To explore the world together, one simple explanation at a time, please subscribe.